Hello and welcome, everyone. Thank you for joining today for this live coding session. So, what can you expect? I want to show you, similar to the last event, methodology to fuzz software with external dependencies. However, today I want to go a little bit more in detail and show you what kind of manual steps are required. So we will make use of the Fuzz data provider a lot. So you will also learn how to use the Fuzz data provider. And I will show you basically how to mock functions using the data from your fuzzing engine. I will show you all this using our tool CI Fuzz, but of course the methodology can be used with other fuzzing engines as well. And in the end, I will also show you, similar to the last event, that a lot of the steps that I will show you today can be automated a lot to speed up this process. But again, today I want to dive a little bit more deeper into the details, what exactly happens in the background. So a little bit about me. My name is Teuchert. I'm a customer success engineer at Code Intelligence. Before working at Code Intelligence, I worked as a penetration tester and information security consultant. And I also, with some others, developed the feedback-oriented grammar fuzzer Nautilus. At Code Intelligence, my responsibilities are to show our customers the value of CI Fuzz. So all the customers that are using our tool, I try to make sure that they get the most out of it, that they achieve the best results using our software. So this includes that at our customers, we need to identify the best approaches to fuzz the code of our customers. So because we will talk a lot about fuzzing, I want to give a very brief recap on feedback-based fuzzing, because this is the kind of fuzzing that we will use. So basically, when we talk about fuzzing, we have a fuzzer that will test some part of software, and it will do so by generating inputs, and then the target software will process these inputs, and the fuzzer will see if the target application crashes or not. With feedback-oriented fuzzing, we also have this feedback loop. So our fuzzer not only provides the input and runs the target software with this input, but it at the same time monitors the behavior of the target application. So it gets some information about which execution or which paths the execution took in the target software, which code was executed and which code was not executed. By getting this information, the fuzzer can improve its input generation. So it can mutate the inputs in a more smart way, so that it will generate inputs that trigger new code paths. So in the end, feedback-based fuzzing leads to a much higher code coverage in the target application. And the higher the code coverage, the higher the chance that we find some hidden bugs in the target application. The most important takeaway for today is that the fuzzer, using the feedback, can learn how it should generate these inputs to that it provides to the target application, so that it can increase its code coverage. To get this code coverage, usually you during compilation, so when the target software is compiled, you need to insert some small snippets, and these you can think of them like sensors that give the fuzzer the feedback and tell them, hey, this part of the software was executed, this code was executed. So this is usually inserted at compile time. So now with this very short introduction in feedback-based fuzzing, let's talk about the challenge that we want to overcome today. So let's say you have a module in your software that you want to fuzz, and you have your fuzzing machine where your fuzzing engine runs on, and this is all run on a Linux machine. And your target software has a public API. So what you want to do is you want your fuzzing engine to call functions from this public API. And when it calls these functions, the arguments should be generated by the fuzzer. So the fuzzer will generate different arguments, execute these public API functions, and see if it finds any crashes or other problems in the target software. And by using the feedback, it will try to call the functions in different ways to get the highest code coverage. But now here we have the problem. The target module that we want to execute, whenever we call some of these public API functions, it might be that our target module, again, also calls a different API, maybe an API that is hardware dependent, or another external API. Maybe usually the target module wants to obtain some values from some sensors, or maybe our target module is part of a bigger framework. For example, in automotive, we often have the AUTOSAR framework. And maybe when we want to fuzz, we don't want to fuzz the whole AUTOSAR framework. And maybe we even cannot run the framework on our fuzzing machine. So this is our problem, because these external dependencies, these functions that our target module wants to call, they are not on our fuzzing machine. We don't have the software that provides these API. We cannot run the software on our fuzzing machine. So what we need to do is we need to resolve these dependencies. So in a way, we need to implement this API ourselves. So we need to somehow create a mocked version of this API. We don't want to recreate all the logic. The important thing is that we need something that takes like the same function names, the same arguments, and returns the same kind of data. But implementing these functions in a meaningful way is very difficult, because maybe you know this from creating unit tests. If you want to run your unit tests, then when you create a unit test, you think about a specific application, specific values that you expect from all the functions that you want to call. But when we want to fuzz, we kind of want to take into account all possible ways that these APIs can respond to our target software. So we need to find a way to implement these functions, this API, so that the response from this API can be everything, even unexpected values. And only if we achieve this, we can really fuzz our target module and be sure that even if this API behaves a little bit weird or unexpected, that our target module still is safe and secure. So this is already what I talked about. This is our approach. So we want to use our fuzzing data to simulate the behavior of these external dependencies. So when we implement those functions, these mocked functions, we want them to return fuzzing data. Because when we use the fuzzing data that we get from the fuzzing engine, the fuzzer can again use its feedback not only to find out the best way to call the public API functions, but it also can use its feedback to find interesting ways how the mocked functions might behave. So it can also find out what's the best way or the most interesting way, and interesting means the highest code coverage is achieved, the best way how these external dependencies should respond. So basically what we want to do is when we have this, when we have a module that we want to fuzz, we want that our fuzzer simulates the complete surrounding of the target software. Not only how the public API is called, but also how all the other APIs that our module makes use of, how these APIs respond to our target software. So in the illustration of before, it would look like this. So it's similar than before. We have our target module here. We have the public API. Our fuzzing engine calls the public API with fuzzing data. And at the same time, whenever our target module calls one of these external dependent APIs, these external API functions. Then our fuzzing engine also supplies the return values of these functions. So this could be, for example, some hardware or network replies. So that's the theory. So let's take a look how this is done, how we can actually implement this. So everyone who was in the last automotive live coding session might be a little bit familiar with this. I created a sample project. Last time it was in C, this time it's a C++ project. So we have different modules and we want to fuzz this software. However, in the software, we have some external dependencies. So here, for example, we have a function called third-party library calc HMAC, and this function is declared as external. So this means also in this case, this function is not implemented anywhere in our source files. So we only have the declaration here, but we do not have the implementation, the definition. This is not in here. And we also have some other functions. For example, here we also have an external defined function called GPS driver obtain current position. This might be like a function that can only be called if a specific driver is installed on your target machine, but we don't have this installed on our fuzzing machine. But we still want to fuzz this software. And this is why we will have to implement these functions in a meaningful way using our fuzz data, as I explained earlier. But let's start with creating a fuzz project. So I'm using a Visual Studio Code here, and I will use CI Fuzz. So we also have our CI Fuzz plugin installed here, and I will create a fuzzing project. This can be done very quickly. Our plugin also automatically identified that there's a CMake file existing here, and actually this CMake list file compiles all the source files into a static library. So we actually can leave it as it is. And our fuzz process when using CI Fuzz is done in Docker. We could supply a specific Docker image, but actually for this case, we can just build in local mode, which uses a very small, lightweight Docker image. So what happens now is we are building our software, and we are building the software with instrumentation. This is very important if we want to use feedback-based fuzzing, because this is the only way how our fuzzer can get the information about the code that was covered. If you would use AFL or libfuzzer directly, you usually have to do this yourself. You have to make sure that when compiling the software that you are using the specific AFL compiler, but in this case, this was all done in the background. But now we are ready to create our first fuzz test. So let's pick a function. Let's start with the verify HMAC function from the scripter module. Now we also have these fuzz this function buttons here. So if I click on this, the plugin already created this fuzzing skeleton. We are using libfuzzer in this case in the background. So we have a fuzz init and a fuzz function here. The fuzz init function is called once when we start our fuzz test. So if we would need to set some global variables or create some objects, we could do this here. But actually, in this case, this won't be necessary. But then we have this fuzz function. And this function is called in a loop. So it's called many, many times. And each time it is called, it gets the input generated by the fuzzer with these two arguments. So the actual generated input is this byte array called data. And size just tells us how large the byte array is with our fuzzing data. So what we need to do is we need to use this fuzzing input, this byte array, to call the verify HMAC function. But if you take a look at the verify HMAC function, we see that this function actually takes 3 different inputs. So first, it takes also a byte array. Second, it takes a size t integer. So this is like the length of this first array. And lastly, it takes an object of type HMAC. And if we take a look at this, we see that this HMAC is actually a struct, not a very complex struct, but yeah, it's a struct. So now we want, in our fuzz test, we want to use the data to be used in all 3 arguments. And to make our lives easier, we will now make use of the fuzz data provider. The fuzz data provider is a single header file. It's part of the LLVM project, and it provides you with a lot of very helpful functions where you can consume your fuzz data in different ways. So for example, we have some functions where we can consume our fuzz data to obtain a string. We can consume our fuzz data as an integer, floating point, or an enumeration. So we will use this fuzz data provider header file to call the verify HMAC function with the 3 arguments. So first of all, let's include it. And also now we have to make sure that the directory where the fuzz data provider is located is also included in the compiler flags. Compiler flags are defined here. So this was all done automatically by our plugin, but now we have to manually add the fuzz data provider directory, which is in fuzzing mocks. So now we can make use of the fuzz data provider, and to use it, we simply first create an instance of it. Let's call it fuzz data. And all it needs is access to the fuzzing data, because this is the data that we want to consume using the fuzz data provider. So now if we take a quick look again, we have this byte array, we have the size t integer, and we have the HMAC object. Let's start by creating the size t length parameter, so then we know how long our byte array should be. So let's create the size t len variable, and now we will make use of the fuzz data provider, and we can simply call consume integral because we want to obtain a part of our fuzzing data as an integer, and this is a template function, so we have to say what kind of integer we want. We want a size t, and that's basically it. So this easy, we can get our fuzzing data as a size t. So the next step would be to generate this byte array. So in this case, let's create it as a vector of u&8t, call it message, and we can create this by using our fuzz data provider, and we can call the consume bytes function, which will return our fuzz data as bytes. We also have to, or as integers, we also have to tell what kind of integers. We also want to have the u&8t's, and we want to have len many bytes, because first we defined how long our vector should be, and now we are creating this vector of this length. And then lastly, we have this struct called HMAC. So for this struct, we actually can first initialize it with 0. So now we have this HMAC object, and all the variables inside of it are 0. But now we want to override it with our fuzz data. So we can call the consume data function. And with this function, we can write our fuzz data at any place in memory. So in this case, we want to write our fuzzing data at the memory location where our HMAC struct is. and we want to override all of it. So we will write size of h many bytes at this location where h is located. So basically, now this struct is overwritten internally with fuzz data. This works as long as you have not too complicated struct, which means if this struct would have some pointers internally, or maybe a v table, then we would have to be a little bit more cautious. We might have to override single members of this struct, but in this case, we can just override the whole struct. And actually, in most cases, it's that easy. So the last thing would be to provide all our generated arguments as the arguments for this function. So first we have this byte array. Second, we have our len of the byte array. And lastly, we have a pointer to our hmax struct. So this is our fuzz test now. If we would not have external dependencies, we could start our fuzz test now. But if we start our fuzz test now, we will get some linker errors because our linker will, or the compiler sees these external defined functions and says, okay, that's not a problem. At linking time, we will see where these functions are. But then when we are linking our software, we don't have the implementation of these functions. So as you can see here, we have an undefined reference error here for this function third-party library calc hmac. And we have another undefined reference error here for the driver get current time function. So the problem is we don't have these functions implemented. So to resolve this problem, we will just go ahead and implement them. So let's create a new file and call it mocklib.cp. So this will be our mocking library where we will create all the missing functions. So all external dependencies will be implemented in here. Because we will use our fuzz data provider here as well, we can already include it here. And one more thing we also need to do is we need to compile the mocklib together with our fuzz test. So again, in our compiler extra args, we need to add our mock library .cpp file, which is in fuzzing mocks mocklib.cpp. So now when we are running compiling our fuzz test, it will be linked together with our mocking library. So now we can actually implement the missing functions. So let's first take a look at the signatures of these functions. So we have the third-party library calc hmac function. So here we can see the signature. So what we need to do is we need to create a function that matches exactly this signature. So we will just copy it from here, putting it in here, and implementing the function. We don't want to recreate all the logic that this function might have. All we need to do is we want to make sure that it returns a value that is actually a u and 8t. So like a very simple implementation of this function could look like this. So in this case, whenever this function is called, regardless of what kind of parameters were supplied, it will always just return 0. It's a valid implementation, so at least this should prevent us from getting this undefined reference error. But we will see later that this is maybe not the best approach when we want to achieve a high code coverage. The second function that was not implemented is the driver get current time function. So let's also copy the signature of this function, putting it in our mocking library and implement it. Again, this function just returns an integer. So also for this function, we can just say, okay, always return 0. And that's it. Now we have these functions implemented. Now we should be able to run our fuzz test, because now when we compile it and link it, because we added it to the compiler args, our mocking library will also be compiled and linked with our fuzz test. So now the linker actually has these references that it's looking for. And as you can see here, the fuzz test is running. We get some basic information about the code coverage, about the executions per second, and about how many different corpus inputs our fuzzer found. So each of these 9 corpus inputs triggers new paths or different paths in our application. We can also take a look at the code coverage. So here, this with the 100%, this is our fuzz test. So this is not really the code coverage that we are interested in. We want to get a high code coverage in these files, the crypto module 1.cpp, for example. But we only achieved 16%. So why is that? Let's take a quick look. Here we can see which lines were executed and which lines were not executed. So we, in our fuzz test, if you remember, we are calling the verify HMAC function. So of course, sorry, let me open the coverage view again. So of course, here we see that we covered this, but somehow we are never executing this part. And in the verify HMAC function, we also see that the calculate HMAC function is called. But in there, we also see we never execute anything in here, but at the very start of the calculate HMAC function, there's a check if the current state is equal to nonce and key set. And this seems to be false every time. So every time we return wrong state, and because then when we return here, we never have, or we always meet this condition that the return value is never HMAC successfully calculated. So this is why we always return here. So if you want to achieve a higher code coverage, we would need to make sure that the state of our application is nonce and key set when we call the verify HMAC function. So in theory, we would have to take a look now at our application. How does it work? So I know to achieve this state, we have to call the set key and set nonce function first. So we can use this to improve our fuzz test and again practice using the fuzz data provider. So we're in our fuzz test, before we call the verify HMAC function, we first want to call the set key function and also the set nonce function. So for the set key function, we need to generate a crypto key. And this is another struct. So we can, again, just initialize it with 0. So let's create an object of type crypto key called k, and we initialize it with 0. And then we will use the fuzz data consume data function to override the content of our struct, size of k bytes. And then lastly, we will provide this struct filled with our fuzz data as the parameter for the set key function. Let me quickly copy these down here because they belong to the verify HMAC function. And let's do the same for the set nonce function. So we want to create a crypto nonce called n. This is another struct, so we will again initialize it with 0, and then we will override everything with our fuzz data. Size of n. Write the n. So now in our fuzzing loop, what will happen? We are creating the fuzz data provider, then we are creating this crypto key struct, fill it with our fuzzing data, and then call the set key function with this input. Then we will call the set nonce function with another crypto nonce struct filled with our fuzzing data. And finally, we will call the verify HMAC function with our with the rest of our fuzzing data with the 3 arguments. So let me stop our fuzz test and we will rerun it. So here you can see the old coverage metrics and the unique corpus inputs. So if we did everything correct, then our coverage metrics should be higher. And as you can see, it's quite, we achieved a better code coverage now. And we also have more different corpus inputs. We can also take a look at this in the code coverage. Let me just quickly rerun the fuzz test so that we can see the changes in the code coverage. 1 second. And then we can again check which code was executed and which code was not executed. So now we see we actually have a much higher code coverage. So in the time module.cpp, we have 100% already. In the crypto module 2, we also have 100%. But here in our crypto module 1, we still have only 79%. So let's take a quick look. Of course, these functions are red because we never call the init or the getState function. We call the setKey function, and because we are providing different keys, we actually achieve all kinds of different states in here. We also call the setNonce function, and we also achieved all different execution states. However, here in the verify HMAC and the calculate HMAC, we still have some red lines that we never executed. So why is that? So for example, in this case, the lines 62 to 66, they are not executed because here in line 56, we are calling the third-party library calc HMAC function. This is the function that we created in our mocking library. And we implemented it in a way that it always returns 0. And here we actually check if the return value of this function is 0. So whenever it's 0, we will just return here. But we will never continue here because our function never returns a different value than 0. So what we could do now is we could change the implementation of this function and say, okay, let's return 1 all the time. But then we still have a problem because then we would never execute this part. So what we want to do is that this function actually works dynamically. And sometimes it returns 0, sometimes it returns different values. And the best case is that actually our fuzzer decides when to return 0, when to return something else. So this is why we will use the fuzz data provider also in our mocking library. So let's improve our mocking library. Let's use fuzzing data in the implementation of our mocked functions and the implementation of our external dependencies. So first, we need a fuzz data provider here. Let's call it fuzz data. And then, because our mocking library needs to have access to the fuzzing data, we implement a helper function. Let's call it mocklib_set_data, returns void. And we just use this function to give our mocking library access to a fuzz data provider that actually contains the fuzzing data. So here, this is like a simple setter function for our internal fuzz data provider. And of course, then we have to call this function in our fuzz test. So here, when we create our fuzz data provider, let's do in the next line, we will provide our mocking library with exactly a pointer to this fuzz data provider. This way, now we can, in here, we can make use of the fuzz data, the fuzzing data, because we have this fuzz data provider. And by calling this function, we can also make use of our fuzzing data because we just set or we just obtained our own fuzz data provider. One more thing I forgot, we need to declare this function because I didn't implement a header file for this function. So let's just declare this function here. Okay, now let's use our fuzz data provider here to return a U&8T byte from our fuzzing data. Again, we use the consume integral function, and we want to return a U&8T. And that's basically it. This is how you can use fuzz data in your mocked functions. You need to give your mocking library access to the fuzz data by using such a setter function. And then you can implement all your functions and make use of your fuzzing data. So in this case, this function also returns an integer. So integer type int in this case. And now the implementation of these functions will not always return 0. It will not always return 1, but the return value is generated dynamically by our fuzzer. And that should be it. Here we are setting, or we are giving our mocking library access to the fuzz data. We declared the function here, so let's try to run the new fuzz test. Let's stop the old one and run the new one. So fuzz test is running, and we also have already one finding. Let's take a look at it. But before this, we can also see now we have a higher code coverage, and we have even more unique corpus inputs. So let's take a quick look at the finding. We found some undefined behavior, and if we take a look at the log, we can see here that we have a signed integer overflow because a very low negative value, we subtract 300 from this. We can also take a look at the exact line location where it happened. So here we see, here we subtract 300. So most likely the very low negative value was coming from here. Let's take a look at this current time function. And we see in here, we call the driver get current time function. And this is one of the functions that we implemented. And so now we found out that actually it might happen that we have some integer overflows here if our external library returns a very low negative value. And if you are dealing with cryptographic stuff, this could possibly have severe consequences. So this might be actually a valid, important finding. Let's run our fuzz test again and take a look at the code coverage. If we now executed the last red parts. So test is compiled and it's running again. And let's take a look at the code coverage. So now we have 87% in this file. And as you can see now, we executed this part because our fuzzer found out that if it returns a different values than 0, then we are able to execute this. One last thing to take into account when creating your mocking libraries is we still have some red parts here. And this is because when this function is called, the only return value of this function, it's not only the real return value, the U&8T, but also this HMAC is actually set to a value. So or at least this is the way how it's supposed to be. In C, you often have it that the functions, they can have multiple return values, not only the normal return value, but also if they get a pointer to some data, they might change the data. And in this case, this function gets a pointer to an array of size 64, and it might change this data, because this is the HMAC that comes from here. That's also coming from here, and this HMAC is used here and compared. So to really improve get the most out of our mocking library, one last step is needed. We want to make sure that this data is also overwritten with fuzzing data. So before returning, we want to call out fuzz data and consume data function. And we want to overwrite the data located at the pointer where HMAC points to. And we know that this is a pointer to a byte array of size 64. So we want to write 64 bytes at the location where HMAC points to, because this is kind of how this function is meant to be called. So the name suggests that this function is called to calculate an HMAC. So it gets a message and the length of the message and a key and a nonce, and then it will calculate the HMAC and write the calculated HMAC at the location where this points to. And this is why when we implement the mocked version of this, we also want to write some data at this location. But in our case, we don't want to write like the correct calculation of a real HMAC, but we just want to write some fuzz data there. We save this, and then if we would run this now, then we could get the last red parts. We would also get them executed. Yeah. Before we take a look at the code coverage, or let's take a quick look at the stats here. So we see our code coverage metrics went up again. So that's a good sign. As I said before, I also wanted to show you that this process can be automated a lot. So like, what did we have to do? We had to find out all these functions that are externally defined, so that are only declared in our software and not defined. We had to find all of them. Then we needed to implement them, and by returning the correct type of data using the fuzz data provider. And we can do this in a more automated way. We created a script for this. So we have this test gen script, which we used to first create an Excel sheet, which we use as a template. And from this Excel sheet, we can generate our mocking library. So to call this script, we need to provide it with all the include paths that we use when we compile our software, so that our script can search through all the header files and also all the normal source files. And then our script will search for all the functions that are declared but not defined, because those are the functions that we need to mock. And if we execute this now, it will analyze our source files. And in the end, we will have an Excel sheet where we can see which functions we need to implement. And in the Excel sheet, we can just give some basic information about the return values. And then we can also automatically generate the mocking library. So this is done now. We created this Excel sheet. Let's take a look at this Excel sheet here. And actually, we don't need this. These are all the functions that are declared and defined. This is here because we also use this script to create fuzz test. But this is not interesting for today. We are more interested in this stub worksheet. And here we see that our script identified 4 functions that are externally declared. So declared but not defined. We also see here we have the 2 functions that we implemented, but it also found 2 more. So it seems like there are 2 more functions in there. If we wanted to fuzz different functions, we would get different undefined reference errors. So to create our mocking library from this automatically, we just have to give some information about the return values. So for example, this first function returns an integer of type uint8t. And same goes for the second and the fourth function. And the third function returns an integer of type int. So this is the return value information. Then we also talked about that we want to override 64 bytes where HMAC points to. We can also write this here. So we can say HMAC, we want to override it with 64 bytes of fuzz data. Then we can save our Excel sheet, and then we can rerun our test gen script. This time we use it to generate code from our from our Excel sheet template. So if I run this now, it will override our mocking library, and we already saw this in the background. So this is our new mocking library. We see we automatically have some all these includes here that we need. We also have our fuzz data provider here. We have this mocklib set data function, which is similar or nearly the same that we implemented manually. We have another helper function here, which is not that important for now. But then here we have the implementation of these 4 functions. And as you can see, it's like the same as when we compiled it or implemented this manually. We also have this consume data function for to override the HMAC struct here. So again, with this automatically generated mocking library, we can rerun our fuzz test just to show it also works. Okay, actually, I did a mistake. Oh, okay, I forgot a semicolon here. Sorry about that. And now our final fuzz test is running. And yeah, it achieved like the same code coverage because we are not fuzzing any more functions, but the mocked library just works the same, and we were able to generate all this manually, automatically. Okay. So much for the live coding. We're also running a little bit out of time, so let's recap what we've done, and then we can have some more questions. So we created a fuzz test for software with external dependencies. These external declared functions. We were using the fuzz data provider a lot, so hopefully you can now use the fuzz data provider yourself. Because it really helps a lot when you want to use your fuzzing data in different formats. We implemented the missing functions using our fuzz data, so now our functions are dynamically returning values based on whatever our fuzzer generated. And in the end, I also showed you that this process can be automated. So basically, you just have to run a script, fill in some information in an Excel sheet, and then you have your mocking library. So in the end, we had a fuzz test that not only used its fuzzing data to generate the arguments for the public API, but also simulated the behavior of these external defined declared functions. So did this fix our problems? So we needed to resolve external dependencies. So yes, of course, we created a mocking library where all the missing defines were implemented, and we even implemented the missing functions in a meaningful way, and we didn't have to like recreate all the logic. But we could just say, okay, our fuzzer uses feedback to find the best way how to respond, how these mocked functions should respond. And that concludes the live session. So let's take a look at the questions. So, okay, the first question I think I should ignore. And the next question, how CI Fuzz supports debugging the case when you detect a crash. So I can show you this. So in this example, so far we didn't find a crash, but let me just quickly introduce a crash. I think if I do this here, then we should have a crash. Here we run the fuzz test. So now we see the fuzz test already stopped, and we have two findings. And if we take a look here, we have a heap use after 3. And now to debug this, first of all, down here we have a stack trace with some information, which data was used after it was freed. And we can also click on Start Debugging here to run our fuzz test, and it will run the fuzz test providing this crashing input. So this input led to a crash. So what we are doing now, we are running the fuzz test, the compiled fuzz test, and we will provide the input that led to the crash. And also, as you can see down here, hopefully, we automatically set breakpoints. And these breakpoints are set to where to other locations that were mentioned in the stack trace. So now you could step through here. You could take a look at all the values that you have here. So you could also take a look what's the value of the current nonce. And this can really help to identify the root cause of bugs. Yeah, and then you could go through here and analyze the crash. Okay. Any more questions? Maybe I overlooked some questions. Let me scroll. Okay. I didn't see any more questions, so please feel free to post more questions in the chat. Maybe also if it helps, this is like the general approach in the end that I presented. So we have our module here, we have our public API, our external API. Our fuzzing engine will provide input to both of them, and we can automate the generation of fuzz tests. And what I showed you today, we can also automate the generation of our mocking library by just filling in some Excel sheets. Okay, seems like there are no more questions. Then, one more question. What will be required to run CI Fuzz for an ARM project? Okay, that's a good question. So far, our CI Fuzz only runs on Linux x86. So if you want to fuzz software that is written for ARM, you could, for example, find out which parts can also run on normal x86. So I think in most cases, even if you have ARM software, a lot of your modules, maybe some modules can also be compiled for x86. And then you could say, okay, I want to fuzz at least these modules. And then we can use exactly this approach. So if you then have some external dependencies that you can only run on ARM, we can just mock these functions, mock these APIs with our fuzzing data, and call the public API of the parts that actually run on Linux in a normal way. Any more questions? Okay, then yes, I would say thank you again, everyone, for joining. If you have more questions later, you can reach out to me on Twitter or contact us. You can also take a look at our blog on our website. And yeah, thanks again for joining, and have a great day.